morning, everyone. Thanks for joining this session. So, as you said, I'm an associate professor at the University of Lausanne, working in particular on cybersecurity and privacy, and I'm especially interested in the cybersecurity risk in machine learning models. So, I think I'm at the right conference today. So, the question of this talk is: can we reconcile machine learning with privacy? And I will start with a mere definition of machine learning from Wikipedia. So machine learning gives computer the ability to learn without being explicitly programmed, and that's what makes it fundamentally different from previous past algorithms where you had to explicitly code every single step, right? Now machine learning enables us to learn from the data directly, right? And this obviously creates an inherent tension between obviously machine learning and privacy, right? If you need to, well, if you want to learn from data and make prediction on data, you obviously need to have access to this data at some point. And obviously nowadays machine learning is ubiquitous. It's useful in autonomous vehicles with computer vision. Is, as you know, now used for large language model with ChatGPT and so on. It's also used in the business domain, for instance, for supply chain management. It's also extensively used in healthcare context. So, obviously, there you have very sensitive data, as you can guess. And it's also used to improve cybersecurity, for instance, to do early detections of intrusion in organizations' networks, right? And so if we need to categorize machine learning algorithms in three groups, we can categorize in this way. We have first supervised learning, where you need labeled data, so data with kind of at least a training stage that are labeled in the sense that we know which class they belong to. This gives us the ability to get a direct feedback to train our machine learning model, for instance, and this is typically used to do some prediction, future prediction or predict an outcome and so on, for instance, estimate a house price. There's also unsupervised learning, where you have, on the contrary, no labels on your training data, so you need to find like hidden structure, more like using clustering approach, for instance. And we have another type of machine learning algorithms, which is known as reinforcement learning, which is more like a decision process where we have a reward function that we need to optimize, and this is typically used in board games, for instance. Okay, so in this talk, I will focus on the first group of machine learning algorithms, which are supervised learning models, which has the one that are been most used and most studied in the security domain. Okay, so in supervised learning, you have training samples for which you know the label, right? The class they belong to, okay? And you use these training samples to actually extract some features, some high-level features from this raw data, and to eventually train a machine learning model, right? Okay? And then once your machine learning model has been trained, someone else can come and upload their data sample for which we don't know actually the label, so there's no label. You extract the model, the service provider will extract some features, the same feature basically as in the training step, and it will return some label that is most likely, right? And if the model is machine learning model is accurate, then it should be the correct label of these samples, or as correct as possible. So a typical prediction example is, will this patient need to be hospitalized for longer than one week based on some raw data samples, for instance, health conditions and so on, right? And this is typically a classification task, a binary classification task, so the answer there should be the label that returned by the machine learning models should be a yes or no, right? So now if we move to security in machine learning. So in security, we have this well-known CIA triad, right? So which stand for confidentiality, integrity, and availability, right? This is well-known. These are the three most important security properties in information and data security. So now if we apply them to machine learning, we should care about first the privacy of the training or test data samples. For instance, if you train a machine learning model with medical records, you have to protect somehow this training data. If you also do at test time, so if you upload some medical records of your patients to an external third-party cloud provider, you need also to care about this privacy of this data. But there's also the confidentiality, the confidentiality of the model itself. If you are a machine learning service provider, you don't want your machine learning model or hyperparameters to be stolen by a competitor, right? So this relates more to intellectual property. Then at the integrity, on the integrity side, you have also the integrity of the prediction returned by the machine learning model that should not be modified, but should, especially maliciously. And we're going to see some examples in the next slide. And finally, we have availability, so in particular, availability of the machine learning system. If you are a business running like cloud-based machine learning services, you want these services to be always available. So now I'd like to discuss briefly in the next slide attacks against integrity of the predictions. So there are nowadays 3 main categories of attacks against integrity of machine learning models. The first one is known as poisoning attack. So in poisoning attack, you try to inject some malicious training data to modify the behavior of the machine learning model that is eventually used, right? And this is especially now through a concern actually with the rise of large language models, to which you could actually give like malicious data to kind of poison the resulting model. And actually, this is not a new issue, right? If you remember, in 2016, Microsoft launched a chatbot that was named Thai, right? And eventually, after only a few days, I think it was totally polluted by kind of extremist ideology, right? And she eventually was writing tweets that were kind of extremist, right? So this is a real concern, poisoning attacks at training time. Then you have attacks at test time that are known as evasion attacks. So once you have a machine learning model that has been properly trained, the idea of evasion attacks is to modify slightly the data that you provide to the machine learning model, like here in these images. So here they have put some stickers on the stop sign to make the machine learning model, so computer vision model in this case that can be embedded in an autonomous vehicle, to make it misclassify this sign as a kind of speed sign. So you see the impact that this can have on the machine learning security and safety of the drivers of these cars, right? So these are evasion attacks, and then finally you have what is known as backdoor attacks. So it's kind of mixed attacks at training time. So at training time, you try to poison a bit the model, so that at test time, actually, if you use a kind of trigger in the data sample that you input to this model, it will always behave the same way. Okay. So for instance, if you put a given hat or a given sign on your face, you provide this image to the machine learning model, it will always classify this image in a given class. Okay. Okay. And for all other benign samples, it will act as expected in a sense. Okay. So now I'd like to discuss more about attacks against privacy, which is my main research interest. So if we come back to this original supervised learning setting, we know that, first of all, there are 2 obvious problems, which is, for instance, if the machine learning model provider point of view, this machine learning provider has access to the training samples, to the raw data, if you want to train this model, to construct this model, and also if you want to make some prediction on some other external samples, you also need to have access to this data samples. So these are 2 obvious privacy concerns, right? And solutions for that are kind of noising the data or encrypting the data. But this also comes with some drawbacks in particular in terms of computational performance. Now there are also issues when you only have access to the labels that are returned by the machine learning model. Okay, and this is for me even more interesting because it looks kind of more difficult to do, and in fact, less dangerous, okay? But there are existing attacks that show that, in fact, you can, for instance, steal the machine learning model by just having access to the labels returned by this machine learning model. This is known as a model stealing attack. And there are also attacks against membership of the training samples, okay? This is what I'm going to discuss in the last 5 minutes, okay? So membership inference attacks were eventually originally developed in the context of databases, where you want to infer whether a target data record is part of a given group of subjects, right? Carrying, for instance, a sensitive attribute. So it can be, for instance, these people here all carry HIV, and you have only summary statistics about these individuals, about this group of individuals. And the idea in membership inference is just to compare the target data record with the summary statistics about this subgroup of the population and the general population that is shown here, okay? And then you just try to see whether the target data record is more similar to the reference data set or the summary statistics to infer whether this data record is a member of this subgroup, sensitive subgroup, okay? And this is linked also to the GDPR and the right to be forgotten, okay? But how about membership in the machine learning context? Can we also run membership inference, so inference of membership in the training data set in the machine learning context? So in machine learning context, as I said, there is the well-known task that is classification. So you train a model with some training data, and then you come with a new query. Someone else comes with a new query with a new data sample and wants to know to which class this data sample belongs. Okay? So what the machine learning service provider will return is typically a prediction that is a vector of probabilities that these data samples belong to a given class. In this case, it's a car that is most likely class this data samples belongs to. Okay? So in a typical settings, you have that kind of cloud provider like Google Cloud, platform, Amazon Web Services, will use a training data set that will remain secret or hidden to construct its machine learning model. And then someone can come and query these models, this machine learning model, through the prediction API. Okay? And the idea is the following to run membership inference attacks against machine learning. If you have an input that has been seen by the machine learning model provider before in the training set, you will get a given prediction vector, prediction probability vector that will be returned by the prediction API. If it's an input data sample that has not been part of the training set, that is, the prediction probability will be probably different. And the idea of membership inference is to try to recognize this difference, right? To infer whether the input data was part of the original training set or not. And how do you do that? Well, in fact, you construct a machine learning model to make this difference, to try to recognize this difference, because this is a simple binary classification task, right? You just need to say whether this was part of the training set or not, right? So you use machine learning against machine learning. Okay, so we got very good results with these attacks, and we were thinking why this was possible. And this is, in fact, possible due to overfitting. So overfitting is a major challenge, a well-known challenge in machine learning. It's the fact that the machine learning model will make better predictions on training data than on other type of other data that was not part of the training set. Okay, so here we have a kind of two problems. From a model utility point of view, we have in machine learning, we need to make the model generalize as well as possible to data outside of the training set, so to all this data here, the universe outside of this red circle. And from a privacy point of view, we need to make sure that the model doesn't leak information about the data in the training set. So these are, in fact, these two questions target the same objective, that is to reduce overfitting. Okay? So to conclude, for once, we see that, well, in the context of membership inference attacks, privacy and utility are not in conflict with each other. Okay? Overfitting is a common enemy, and because overfitted machine learning models lack predictive power, and also overfitted models also leak information about the training data. So the objectives that remain on both sides is to increase generalizability and accuracy of the machine learning model, and also protect privacy. So whereas we tend to think that utility and privacy, you have to trade off utility of your machine learning model for privacy in general when you do a privacy-preserving machine learning model. In this case of membership inference, you don't need to, and they all converge to the same objective of reducing overfitting. Thank you.
Thank you.